Hello everyone, and welcome to Engineered to Ask, brought to you by the College of Engineering here at the University of Nevada, Reno. This is your host, Anthony Kuhl, and today with me is Dr. Aditya Nair, Assistant Professor of Aerospace Engineering in the Mechanical Engineering Department. Thank you for joining us on the podcast today. How are you doing?
I'm doing great. Thank you for inviting me to speak at this podcast. I think you're doing a very important job of encouraging the new generation of scientists and engineers and the Nobel laureates, like whoever is listening to this. Thank you so much. I am so happy being here.
So today we're going to dive into the world of aerospace engineering and technology, and Dr. Nair is going to help us get a better understanding of what we can look forward to seeing in the future from this field of science. But before we get into our main topic today, why don't you tell us a little bit about yourself and what brought you to the field of engineering in the first place?
Thanks for asking, Anthony. So, as you introduced me, my name is Aditya Nair. I am an assistant professor in the Mechanical Engineering Department here at University of Nevada, Reno. And most of the work that I do is in aerodynamics. And I remember when I was a child, I was fascinated by things that fly, including Superman. So I had this crazy fascination of Superman, and I even chipped my tooth diving from my bed or whatever. And I still have a chipped tooth. But, for me, things that fly and things that, like flow, fluids all around me, all fascinated me. And I would love watching birds, love watching airplanes and jets and whatnot growing up. And I used to always think, how cool would it be to design something like that one day? And I think for me, like my journey always began in a way where I loved flight, loved airplanes. And then in engineering during my bachelor's, I encountered one of the most tougher subjects, which was fluid dynamics. Quite honestly, I was good at everything else, but that subject was hard. And I think that is what motivated me, because I wanted to learn more about it. I wanted to know why it's that hard to understand it. And that became my career. So I really enjoyed learning about fluid dynamics. So I did my master's at University of Michigan in fluid dynamics. And then I went on to do my PhD at Florida State. I went on to do my postdoc on it, all in fluid dynamics as a domain, which kind of helped me get a better understanding and appreciation for how fluid flows, why it's important to understand fluid flows, for understanding how we fly. And here we are. Like here I run a fluid dynamics group at University of Nevada, Reno, and we dive into things that interest me and possibly the world in terms of building more efficient, safe, aerodynamically great airplanes. So.
Wow. And I think that actually leads us perfectly into our main topic of today,
Yeah.
Aerospace. So now I think obviously the first thing that comes to mind for most people when we talk about aerospace is like rockets, sort of the things that, the type that we sent up into orbit and the type that got us to the moon in the first place. But we've been working in this field of engineering for decades now, since we first lifted up off the ground and into space. So what's your opinion on like the current state of things when it comes to the field of aerospace? And are there any like recent breakthroughs in aerodynamics that you think are exciting?
Yeah, that's a fabulous question, Anthony. So I think the evolution really, you mentioned rockets and launching. I remember, watching some of these launches or rewinds of these launches on YouTube and things of that nature. And, I used to get fascinated by how difficult it is to launch a vehicle in space. I think with the latest technology and with things how it has evolved, like companies like SpaceX and teaming up with NASA, of course, they are able to do this much more frequently now, which is one exciting.
Yeah.
And with also like commercialization playing in, like there is Blue Origin, there's all of these startups that have started in terms of space exploration that has caused a huge boom in like understanding, or launching vehicles into space, firstly, and satellites, as I believe the entire last 2 decades was getting more internet connectivity because of the internet boom. So you really wanted the, GPS, and you wanted all of these things that we take it for granted when we, just put a map, or like, we just say, okay, we want to go to this destination, but we take it for granted. But that's coming from a satellite that has gone into space, somehow. So I believe, with how technology and times have evolved over time, I think it is also a need. And also, like, we are now interested in exploring mass, exploring space, what is out there, and learning about that. And so I feel like, I'm a big fan of Neil deGrasse Tyson. So when he talks about space, I always, I get enchanted by all of the wonders that is waiting for us to learn from.
I love listening to him as well. Like,
absolutely.
Just any of his lectures are great.
Absolutely. I agree. So for me, like, so you specifically asked about some of the things that lately we have, that innovations that are super interesting. For example, is X-59. This is a partnership by NASA. I believe Northrop. You have to correct me or edit it if I'm wrong here. Yeah. But X-59 is essentially a quiet, supersonic vehicle that they are building, basically, which is super interesting because when we think about supersonic or things that can cross the sound barrier, usually they are extremely noisy and very difficult to build and or to quieten the sound, that is. Now, I'm a big fan. I mean, I'm sure you also watched Top Gun, right?
Oh,
Tom Cruise goes into Mach 10 and I'm like, wow, that's amazing.
Yeah.
Right? But building quiet supersonic airplanes is hard. Right. So X-59, the project that is it's been undertaken is a revolution in terms of, like, they have done extremely beautiful aerospace, and aerodynamic engineering to be able to quiet that sonic boom. And they are claiming that the noise that it produces is just of your door shutting. The sonic boom.
That's
sound.
Actually insane.
That's
Wait, that
insane.
level of quieting?
That level of quieting. And that is purely streamlining of bodies and purely aerodynamics. So just understanding aerodynamics and what streamlining of body does can quieten a supersonic aircraft, to me, is fascinating in the first place, right? Second, I would say is now there is, of course, all this research into sustainability. So there is this hydrogen electric vehicles that are being built, which is hydrogen fueled in some sense. And that basically helps us, build much more vehicles that we can launch in space. Because if we can launch vehicles with much more efficient power, in a way that, it doesn't take up like all of the monetary value of launching it, because as Elon says, if you've watched his recent interview, like launching these vehicles is costly, essentially, right? Like powering these vehicles up to space is really costly thing. So if you can make technology that is able to navigate that would be amazing, right? Mm-hmm. So there is this hydrogen electric vehicle space, which is in sustainability, and then there is a rocket-powered space. And people are innovating in both of these areas. In rocket-powered, also to basically launch vehicles much more efficiently, space vehicles much more efficiently. Mm-hmm. So there's lots of innovations in terms of, going from, okay, how do we fly, or how do birds fly, to how do we make this as safe, as efficient, as sustainable as possible. Mm-hmm. And I think that is where I see the evolution going towards, is building the next generation vehicles that are much more sustainable and doesn't, destroy the environment with all of the carbon, if I may say. So, yeah.
Yeah. That's so interesting to hear, like, the fact that there's almost, like, I want to say dual research going on at the same time between like the two different fields of, like, focusing either on rocket powered ones or on hydrogen powered one. That's really interesting.
It is. And I think that to me is, like, I mean, those are the cutting edge, right? Like, I'm talking to you about the cutting edge in 2024. Now, what is the cutting edge in 2028? That landscape may look completely different. And I feel like that is powered through engineers looking at, the fundamental aspects of these problems. Like, why is one more efficient than the other, right? Now, of course, like, you would say, okay, a Tesla is more quieter because it has, battery power, it is more sustainable. Is there something even better than that? Like, I think it is about asking those challenging questions that we wouldn't ask. We sometimes, as engineers, if we take things for granted and just take the current technology as the thing that we are supposed to just go forward with, I think we're losing out on a lot. And I feel like that is why I, as a professor, have a unique opportunity to think about these problems that really affect affect future engineers from creating and innovating, right? Because there are also barriers to entry of why certain technology works and why others don't. And usually in the aerospace space, that can mean, translating what we learn or research into actual technology that goes on an airplane can take a long time, actually, sometimes, right? But with the speed of innovation, with commercialization, I believe there's a lot of opportunity in terms of testing these ideas. So it's a very exciting time to be in aerospace, to be honest with you. So
wow. Yeah, and that's great to hear that there's like this great drive still to like reach the stars like we did beforehand. And I think at this point, it's a good chance for us to ask, what kind of work have you been pursuing here in the College of Engineering?
Yeah, thank you for asking, Anthony. So, of course, like, I'm an assistant professor. My main job is to teach and train the absolute best, the young scientists, the young engineers, and teach them what I know. And of course, I don't know everything, but at least what I have gathered over time as to what is important in terms of aerodynamics, in terms of fluids, in terms of engineering. So I think for me, the most exciting thing here is teaching the next generation. So I do teach a class in aerodynamics, which teaches students about the fundamental principles of aerodynamics, and I teach a class in gas dynamics, which is high-speed flows, which is basically, if we wanted to go towards supersonic speed, what are some of the key principles that you need to know? Now, in addition, I do teach classes also in numerical methods. So my group that I run here is a computational group. So for me, learning about coding is very, very important. So if I had one piece of advice for someone who is interested in computations, is to get really good at coding, is to understand, not necessarily learning all the syntaxes, learning everything about everything. It's about being able to read and understand code, and that's a unique skill, I feel like, and that can help you in many different ways, right? So in numerical methods, I try to teach how principles of coding and how to build numerical algorithms to understand or solve complex mathematical problems, right? So in my group here, it's a blend of doing computations. So I do computations, which involves a lot of math. I do high performance computing, which involves a lot of understanding how clusters work, right? So not just a single computer, but how does a supercomputer work? We have codes, or we build codes that work in using GPUs, for example. And the next, leap is going to be in quantum. So I have to adapt and I have to learn myself to go towards quantum, for example, right? Which is gonna come sooner or later, because that is the most efficient way of doing computing, for example. So in my group, we combine ideas of computing, like I said, or building mathematics, building algorithms, or high performance computing codes, and they're all catered towards understanding unsteady aerodynamics better. There is a huge space in fluids where we want to understand aerodynamics, but we also want to understand the coupling between fluids and structures. So if you launch a vehicle in space, there is usually an interaction that's happening between what the fluid is doing, or what the air is doing around you, or whatever medium in a different planet is doing around you, and the vehicle that you're interested in. So there is this complex dynamics that can cause the structure to do weird things, right? Mm-hmm. And especially, this idea of understanding fluid structure interaction is quite complicated. So in my group, we try to understand fluid structure interaction. We try to understand high-speed flows. So we do a lot of supersonic flows in my group, and unsteady turbulent aerodynamics, which is also very complicated. So all of these are fundamental problems, but they are applicable in diverse disciplines. And the three prongs that we study in our lab is to understand the physics, is to model the behavior of the system, and to do control, which is to optimize the behavior of the system. So usually I'm doing coding, or we are doing computations, and then we are doing machine learning or AI. We are using modeling tools. So in some sense, we are quite a modern group that uses latest innovations in data-driven science. We also are traditional because we need to obey physical laws, physical constraints, understand what is happening to the physical system. I'll give an exciting example. This is a recent work by my student, where we start to understand how very, very small variations in the physics can lead to catastrophic changes in the system. So for example, there is a phenomenon called aeroelastic flutter. And flutter is where you could have a disturbance that affects the wing. And what happens is this disturbance can actually cause the fluid to dump energy into the structure.
Really?
And when it dumps energy, the structure can vibrate really unconditionally. So in some sense, that can cause the structure to completely fatigue and break down in some sense.
Yeah.
So understanding a phenomenon like aeroelastic flutter is crucial, because when we have these vehicles and these launches, and if something like a sudden impact or disturbance happens, you can have drastic changes in how the structure responds.
Yeah, the
and that may
structural
result
behavior.
yeah, exactly, and that may result in a catastrophic loss. So understanding these things and having safeguards to not have that by designing control strategies is critically important in aerodynamics. So we try to accelerate simulations and computations using or building new algorithms for doing that. So instead of using a supercomputer, can you design something on a laptop? That is one thing that we're interested in. So accelerating the design process in general for these complex problems, modeling these systems, and doing control. So yeah.
Wow. And so I think actually that leads us perfectly into the next line of questioning, and I think we kind of answered it here, is, what fields do our students need to be looking at getting involved in if they want to be a part of the aerospace fields? It sounds like it's a lot of not just physics and basic mathematics that we usually have. I have a background in mechanical engineering and computer science, so it sounds like having that extra background in computer science is a total benefit to going into that field.
So for me, I am quite biased. I love math, right? So for me, appreciating mathematics, not just for, when we learn math, it's quite dry in some sense, because these are just tools for you to learn. But I believe when you become an engineer and when you start doing design, you start to really appreciate the power of mathematics, because mathematics naturally leads into understanding coding better, right? Because it leads to logic.
Yep.
If you can translate mathematics to logic and code, that can help you build something really cool that you would have not thought about before, right? So for me, there is this, I don't think science is a single field anymore. I feel like in terms of engineering and science, it has evolved where you really need the interdisciplinary power to kind of learn different things. I'll give you an example. So in my PhD, when I joined, my advisor, he's Japanese. He's one of the coolest researchers in the world. And, when he hired me, he actually hired me to build a simulation platform that is able to accelerate computing. So one of the prongs that I told you that I was interested in Nevada, Reno as well. But I know that one day he was driving, and this is the story that he tells me, and he learned about this beautiful mathematics of graph theory on NPR. And he came back to the lab and he said, have you heard about graph theory or network science? I told him, I have very limited idea of it. And he gave me a book on network science, and he basically told me, why don't you read it? See if there is something interesting here. And you won't believe it. That became my PhD thesis.
Really?
I did my PhD thesis on network analysis of unsteady fluid flow. So instead of thinking about social networks, I thought about fluid packets as networks and build models understanding how they interact with one another. So, I mean, this is to just say that you don't know where the ideas are coming from. So being interdisciplinary, being flexible, probably gives you the best edge in terms of innovating for the next generation technology. So.
Wow. Thank you so much for coming on the podcast today, Doctor. And a big thank you to everyone who's listening out there. We greatly appreciate you stopping by. If you'd like to know how you can get involved with this sort of research and more here at the University of Nevada, Reno, you can visit our website. The links will be in the description. And if you liked this discussion and would like to hear more about other interesting engineering-related topics, please like, comment, and subscribe. It's the easiest way of keeping up with the series and letting us know that we're doing a good job. Until then, this has been Engineered to Ask.